So last class we were working on that integral functional. So we were taking the exam. No, the last example I was working was example of Euler-Bernoulli beam problem. And the last thing I had done was that finally I had set the big form. So if you look at the last lecture, so big form, after making some denoting some various secondary variables in terms of shear force and bending moment, we have written this as uh, this small v is the transverse deflection of the beam and capital V is shear force. So this was minus delta VL into VL. So this I had written, so I'm just writing it again. So we had delta of dV by dx is slope at x equal to 0 into bending moment at x equal to 0 minus delta of dV by dx at L into bending moment at L. So this is what we had written, plus we had this integral term, integral 0 to L delta of we said that the variation operator and the differential operator are interchangeable. So under that we wrote this as uh, delta outside, and then EI d2v by dx square dx minus integral 0 to L delta v q dx. You can actually know you to arrive at this expression, this big form, rather than first taking the weight function as w and then taking w equal to delta v, you can from the beginning also, for the purpose of deriving the integral functional, you can take w as delta v directly, and then you can work on you will arrive at the same expression what we have got over here. You will find that weak form we can derive for any problem, and aim is always to know equally distribute the derivative between the weight function and the unknown variable. So that is what we do. And if the differential equation is involving, say, the 1D problem, if the differential equation is involving even order derivatives, then we can equally distribute the derivatives between the weight function and the variable unknown variable. But if the differential equation is involving odd order derivatives, so in that case, you will not be able to obviously distribute the derivatives equally between the weight function and the known variable, because it involves ordered derivative, say first derivative, third derivative, fifth derivative. Then you will not be able to distribute the different derivatives equally between the weight function and the unknown variable. So in that case, you leave the weak form as it is, and you also need to look at how many times we need to do the integration by parts, so that we decide based on it should give physically meaningful primary and secondary variables. So the integration is basically done according to that. So for the problems involving even order derivatives, you will be able to get the integral functional. But if the problem is involving odd order derivatives, then you will not be able to get the integral functional. So that's the another thing you will see. So now in this problem, we take the variational operator delta common. Delta is a operator. No, keep in mind that this is not a quantity, but it's a operator. So as I explained last time that we are treating V naught, VL, M naught and ML as known quantities, so their variations is 0. So from these terms we can simply take out the delta common. So we will have V naught into V naught minus VL into VL, plus we will have dV by dx at x equal to 0 into M naught minus dV by dxl into ml. So this is what we will have, and from this term, when you are taking delta common, so as we did last time, we will have half and integration 0 to L, and then we can write ei and then d2v by dx whole square dx. So this is what you will get when you take the delta common from this one. So obviously, when you bring in the delta inside, this is a known quantity, so its variation is going to be 0. So the variation of d2v by dx, so whole square will be 2 into dv by d2v by dx square into delta of d2v by dx square. So 2 and half will cancel out, so we will exactly get this term. So this minus integral 0 to L, and the last term, because q is a known quantity, so its variation is 0, so only we will have just v into q dx, and this whole thing is equal to 0. So we write this as delta of I equal to 0, and where no, the integral functional I is nothing but what we have written inside the bracket. So where integral functional I is equal to, let me first write this strain energy term, so which is half of integration 0 to L ei d2v by dx square whole square dx. Then let me write this potential of transversely distributed load dx, and then of course the potential of other terms v naught into v naught minus vl into vl plus dv by dx naught m naught minus dv by dx at L into ml. So this is the integral functional. And why it is integral? Because it involves integration and functional. So see why the functional means a function of function. So if you see here, v is a function of x, because v is going to vary along the length of the beam, so v is a function of x, and then this I is a function of the v and its derivative, so it's kind of function of functions. So that is why it is known as functional, so we call it as integral functional. And now let's look at the interpretation of the various terms as we did for the rod under axial load. So similarly, let us try to interpret the various terms here. So in of I. So physical interpretation of terms of I. So first term is nothing but actually strain energy. And as I said, no, this I is also referred to as total potential energy functional. Integral functional or total potential energy functional. So the first term is strain energy. Let me show you how, if we were to write directly this integral functional, how do we write that? So to explain you why the first term is strain energy, so you take the Euler-Bernoulli beam, let us say, and this is of course the x-axis of the beam, this is y-axis, and in this direction we have the displacement v. So this is the beam in the undeformed configuration, and let us say this beam bends and takes no, this becomes its deformed configuration, and this is the deformed center line. This is the deformed center line. Now suppose if you take a, any no normal to the middle surface. So initially let us say this is the normal what I have drawn. This normal is basically normal to the longitudinal central line, this line, and I am extending this up to here. And then now if you look at as per the Euler-Bernoulli beam theory, if you look at this normal, this one, now this takes us, it rotates and remains normal to the beam. So this is the deformed center line. Now the normal becomes like this. So this will be the normal. So that is this line, which is this line over here becomes this line, and it remains normal. So that means this angle remains 90 degrees, and this therefore this angle, this particular angle would be dv by dx. So if I want to look at the displacement of any point, so suppose I had a point over here and this point now has gone over here. So the displacement of this point is nothing but basically this distance. So if you look at this distance, this is the displacement of the point. So if I look at the displacements, so one is the axial displacement. So u, which is a function of x and y, will be equal to, because I have said no this distance, so that can be written as it is at a distance y. So and it's along the negative x direction, so minus y into angle. So we are assuming that this angle is small, so rotation of the normal is small, so therefore the distance can be written as just simply y into dv by dx. So v is a function of x and this y is coming, therefore your u is a function of x and y both. And of course you have the transverse displacement, that same point gets displaced along the y direction. So this is and that is assumed to be only function of x. So these are the displacements. Now if you look at the strains in case of beam, so we are looking at beam. So the strains are only independent non-zero component of strain is epsilon xx, and as you know this is del u by del x, and as you know u is this given by this expression, so it would be minus y into d2v by dx square. So this is the strain. Of course, we are assuming that the displacement gradients are small, so we are only taking the linear term and then we are writing this strain as epsilon xx is equal to minus y into d2v by dx square. And actually, this term d2v by dx square is also referred to as curvature. So that is 1 upon radius of curvature. So this is known as curvature. That is d2v by dx square. And so suppose similarly if you look at the stress, so stress is sigma xx. We are assuming that the material is linear elastic isotropic, so for that stress would be Young's modulus into strain, and which can be written as minus cy d2v by dx square. So this is the strain. Now if we look at the strain energy, so I'm denoting the strain energy by pi. So pi, as we know, half in this case integration over the volume, and we will have only one non-zero term sigma xx into epsilon xx, because all the other stresses are zero. So this is dv equal to 0 because this is uniaxial state of stress. So uniaxial state of stress means sigma yy, sigma zz, tau xy, tau yz, tau zx is equal to 0. So this is uniaxial state of stress, and that is why we have in the strain energy term only one term, that is half of sigma xx epsilon xx integrated over volume. Now this integral we can split into integration along length of the beam and integration over the cross section. A is the cross section of the beam. So the cross section could be any shape. The cross section of the beam, say it is any shape of the cross section. So this is y coordinate and this may be z, and we are taking any differential area dA in the cross section. So this is your dA. So integration over the cross sectional area, and sigma xx you can write 3 times epsilon xx, so it becomes c times epsilon xx into epsilon xx, so that is square, and then you have dA dx. So you are splitting this integral in this manner, and then therefore half of integration 0 to L integration over area E, and then epsilon xx we have already written. This is the expression for epsilon xx. So when you square that, minus sign will go, so you will have y square d2v by dx square whole square dA dx. So now in this what you can do is half integration 0 to L and integration over the cross section. So we have e y square dA we can, because this is the only function of the cross sectional coordinate, and then d2v by dx square of course is only function of x, so we have this dx, so you can write it like this. And now see, when you are looking at this, so y square dA, integral of no y square dA over the cross section. So dA is the area, y square is the square of the distance from the z axis, that is the neutral axis. So you would see this is the second moment of area, so half integration 0 to L, and then that can be written as E into I d2v by dx square whole square dx. So this is exactly the what we got over here, the integral functional when we arrived from the differential equation. So this one, so you can say that it is nothing but actually exactly the strain energy. So strain energy we have written from here, this expression. So yeah, so that's the first term. Now if you look at the second term, so second term is, so you have this beam y and v, and then there is a distributed force along y direction, which is a transverse force, that is q. So if you take a differential length of this dx, so if you look at the force over this length, it is going to be basically q into dx, and that any x, the displacement is v. So v is the displacement along the y direction, and force q is also along the y direction. So v into q dx is the work done by this force q acting over a length dx, and the potential energy is negative of this, taking datum as the undeformed configuration. So we put a minus sign, and then to then get the total potential energy, we integrate it from 0 to L. So you would see that this is the potential of distributed force q. Potential of distributed force q with datum as the undeformed configuration. Datum means the configuration at which the potential is 0, with datum as undeformed configuration, when the beam is undeformed. Now the other terms, if you look at the other terms in the integral functional, are the total potential energy functional we have got. So that is, if you look at this term, this term, this term, and this term, so these four terms. So let me discuss all the four together. So I'm just writing them as other terms. So first let me show again these forces and the corresponding displacements and rotations. So right side we have the shear force, which is VL, capital VL, and because the coordinate system is this is x y, so we have the shear force is along positive y direction here, and this is the ml bending moment. This side the shear force is v naught, and bending moment is about moment about negative z axis, so that is m naught. So these are the forces that in the beam. Depending on the boundary condition, these would be, some of these would be 0, non-zero, depending on how the beam is supported. If you look at the end points, the displacements, so the displacements are here, no, the displacement is VL, and the rotation would be dv by dx at L. Similarly here the displacement is v naught, and the rotation is dv by dx naught. So these are the deflections, and so depending on the boundary conditions, so say for example, if we have a cantilever beam, so left end, let's say it is fixed, so there no this small v naught and dv by dx naught, they would be equal to 0 at the left end, and at the right end, since it is free, so the shear force and the bending moment at the right end should be 0. So depending on the boundary condition, these terms can be 0 or non-zero. So I'm writing for a general case. So now essentially the all other the remaining terms are but nothing but potential of these. So let's take one by one. So if I take this shear force on the left hand side, which is capital V naught. So see, this V naught is in the downward direction, whereas no, this displacement the left in small V naught is in the upward direction. So if you look at the work done, so the work done is going to be minus small V naught into capital V naught, and then the potential energy is negative of this. So we get a minus sign when we write the potential energy. Now if I look at the right side, so the shear force is in the positive y direction, and the displacement on the right hand side is also along the positive y direction. So both of them are in the same direction. So the work done would be small vl into capital VL, and then the potential energy would be negative of this. Then if you look at the now the moments, so if you look at this m naught is about negative z axis, whereas this dv by dx naught, that is the rotation slope, is along the positive z direction, because this is xy, z axis will be coming out of the screen. So you will have this is about the positive z axis, this is about the negative z axis. So the moment and rotation, they are in the opposite direction. So the work done would be minus dv by dx naught into m naught, and then the potential energy is going to be negative of this. Potential is always negative of the work done. Then finally we will have this moment ml. This is about positive z axis, and this rotation is about positive z axis. Their product gives you the work done. So the potential energy is minus dv by dx at L into ml. So you will see that this is equal to V naught into capital V naught minus VL into capital VL plus dV by dx naught into m naught minus dV by dx at L into ml. So you will see that this is the potential of in forces and moments. Potential of in forces and moments. Forces means shear force and moments means bending moment. So you would see this is how so far different problems given a differential equation. Of course, it should be basically the differential equation involving even order derivatives. You will be able to get the integral functional, and this is how you do. So now the next thing is, so far see what we have done is we have discussed the approximate analytical solutions directly based on the domain residual RD. So that we have discussed. Then we have also discussed big form, and then based on big form, how can we obtain the analytical solution, approximate analytical solution of differential equation. And now since we have also talked about this integral functional, so there is another method for finding out the approximate analytical solutions known as Rayleigh's method. So let me discuss that next. And I think with that, once we discuss the Rayleigh's method, then we come to the end of approximate analytical solutions. Then we will move on to the finite element method. So in the what we do here is in the approximate analytical solution using what is known as the Rayleigh's method. Rayleigh's method. So let me first write down the three main steps which are involved in this. So step number one is that assume an approximate solution. So this is more or less similar to what we do in the big form based approximate analytical solution. So assume an approximate solution different. Now only thing is we'll have to see the differentiability requirement. So differentiable at least up to the highest order derivative present in the integral functional. Now we look at highest order derivative of unknown variable in the integral function present in the integral functional present in the integral functional. So that's the first step, and this is same as what we do in the weak form. So as you have seen, there also be assume an approximate solution which is differentiable at least up to the highest order derivative present in the weak form. So the highest order derivative of unknown variable in the weak form and the integral functional is going to be the same. So we will see that this is basically going to be the same what we do in the weak form. Then the second step is, as we do, we eliminate some of the unknown constants uh, so as to satisfy the essential boundary condition. And the same thing we did in the weak form based solution also. So eliminate some of the unknown constants so as to satisfy. And now we know what is the meaning of essential boundary conditions. Essential boundary conditions. And then the last step, third step is find the remaining unknown constants by minimizing the integral functional. Find the remaining unknown constants unknown constants by minimizing the integral functional. So these are the three steps which are involved integral functional I, what we have already discussed. So this this is what no these are the steps involved. Now let me take the same example again. What I am doing is across all the methods I have been taking these two examples, and of course when you go through the assignment you will learn how to do it for the other cases. So it is essentially going to be the same, steps are same. So example one, I am taking this rod under the axial load. So one end of the rod is fixed, so this is x, and the corresponding displacement along x direction is u, and there is a distributed force q here. Length of the rod is l, and the cross sectional Young's modulus into cross sectional area product is a, and as we said earlier, a and q constant along length, constant, although it's actually not necessary along x, but for the timing I'm assuming that. So now we have already derived, now if you remember for this problem also we have derived the integral functional, so which is strain energy term half integration 0 to L, and then we have EA into du by dx whole square. So this we have done, no, we have derived this, minus the potential of this q, so which is integral 0 to L u q dx. And if you look at the other terms we had where basically we had this one term is plus u naught into q naught minus we had ul into ql, this term. So now if you see at x equal to 0, u is 0, so u naught is 0, so therefore this term would be actually 0. And at x is equal to L, that is at this end there is no externally applied load, so this QL will be 0, so therefore this term is 0. So this is what you have. And now we assume an approximate solution. So now if you look at the highest order derivative of u present in the integral functional is the first derivative. So we assume, if we assume a polynomial, we need to assume at least a linear polynomial. So we take a0 plus a1x, and of course we include a0, so that's a complete polynomial that you have constant term and a linear term. Now if you look at the essential boundary conditions for this problem, so boundary conditions are u equal to 0 at x equal to 0, and here no, the boundary condition is that du by dx equal to 0 at x is equal to l. So the essential boundary condition, because for this problem we know primary variable is u, so prescription of u is essential boundary condition, so that is only this one. So u equal to 0, essential boundary condition is u equal to 0 at x equal to 0. So this implies, no, if we put x equal to 0 here, we only get a naught, and that comes as a naught equal to 0. So therefore finally you will get u simply as a1 into x. You will notice here that this function x is satisfying the homogeneous form of the essential boundary condition, whatever function we are getting over here. Now we substitute this approximate solution in the integral functional. So with respect to x, anyway we are going to do the integration. So finally you would see that I will be function of, this unknown constant a1. So I as a function of a1 would be half integration 0 to l du ea, and du by dx is simply a1, and its square would become a1 square dx, and minus integral 0 to l u is a1 into x q dx. So this is what we have. So you find that I of a1 is equal to the first term integration. We are taking ea as constant along x, so this will give you simply half eal a1 square after integration, and the second term will give you basically the ql square by 2 into a1. So this is your ia1. Now for minimum of I, for minimum of I, di by da1 must be equal to 0. So di derivative of I with respect to a1 must be equal to 0. So that will give you, so now if you differentiate it, so you will get, here the unknown variable, we are differentiating with respect to a1, and these are all constants. So we will get here eal and 2a1, and 2 and half will cancel, so we will just get a1, and the second term just a1 would go, so ql square by 2, and this is equal to 0. So from here you will get basically a1 is equal to ql upon 2ea. So yeah, this is one way of looking at it. The other way of arriving at the same result is that we say, because when we came from the weak form to I, so we have actually written this condition. The weak form is equivalent to saying that delta of I equal to 0. So now if you look at the same I, if you want to look at its variation, so this is your I, which is a function of unknown constant a1. So when we take the variation with respect to a1, so we will have to differentiate it with respect to a1, and then the variation of a1. That is what would be the variation. So now the first term derivative, so I can write that as basically this delta of I can be written as del I by del. In this case it is actually a function of only a1, so it's a total derivative. So I can write this as di by da1 into delta a1. So that is how I can write this is equal to 0. And di by da1, so the first term will be, we have already looked at that, eal into a1 minus we have ql square by 2 into delta of a1. So this will be there is equal to 0. Now see, this delta a1 is arbitrary, that is not equal to 0. So since delta a1 is not equal to 0, so therefore for this equation to be satisfied, we get eal a1 minus ql square by 2 equal to 0. So the same thing but written differently, and therefore I know you get a1 is equal to ql upon 2ea. So therefore I know you will see that the final solution is going to be u is equal to ql upon 2ea into x. So this is the final solution. So this is if we take the the assume approximate solution involving only two terms. That is, we have taken basically no a0 plus a1x. We can actually for better accuracy we can increase the number of terms. So the next you can also say look at let u for better accuracy, let u will u be equal to a0 plus a1x plus a2x square. So this is we have increased one more term. The minimum required was this, and for better accuracy we have added one more term, that is a2x square. So now we look at the essential boundary condition, and it is not necessary that you always assume polynomials. You can assume the solution in the form of trigonometric functions. You can assume the solution in the form of Legendre polynomial and things like that you can do. So essential boundary condition is u equal to 0 at x equal to 0. So this will imply when we put this side x equal to 0, we simply get a naught and that is equal to 0. So therefore finally we would see for this case the solution is a1x plus a2x square. So sometimes you will, in the literature you will see that this can also be written as ai into phi I, where I is going from in this case 1 to 2. So if you look at a1 and a2, these are the constant, and phi 1 is nothing but x and phi 2 is nothing but actually x square. So you will see that this always you will, after satisfying the essential boundary condition, whatever approximate solution you have, so the coefficients of unknown constants will always satisfy the homogeneous form of essential boundary conditions. So this satisfies homogeneous homogeneous form of essential boundary conditions. So what it means is that now say now right now we have the essential boundary condition is u equal to 0. So you will see that right hand side is already 0, so it's a homogeneous form. We could also have say u at x equal to 0 as some u naught which is non-zero value. So the homogeneous form of that would be u equal to 0. So you will see that phi 1 at x equal to 0 is 0, so it is satisfying the homogeneous form of the essential boundary condition. Similarly, phi 2 is x square, which is 0 at x equal to 0. So this is also satisfying the homogeneous form of the essential boundary conditions. Now, if you look at this approximate solution, it is a function of two constants a1 and a2. So when we substitute this in the integral functional, after integration, that would be function of only these two constants a1 and a2. So you will get I, that is integral functional or total potential energy functional, which would be function of a1 and a2, and this will be equal to half integration 0 to L, and then we have EA du by dx whole square, and du by dx would be a1. This is a1 plus 2 a2x whole square dx. So that's the first term minus integration 0 to L, and we have u into q, and u is a1x plus a2x square into q dx. So you have to integrate this, and no, I'm not doing the integration, so I'm leaving this as a homework problem. So you must complete this. So after no integration you will have to know square this term and then integrate it with respect to x. Similarly integrate this with respect to x. It's a straightforward thing. And after no you get the I as a function of a1 and a2, then no the solution you will get del from del I by del a1 equal to 0. Now these will be the partial derivatives, So you will have to I think, yeah, so I hope you can do the partial derivative. So let me do, I think so, rather than leaving it. So let me complete it. So I as function of a1 and a2 will be equal to half integration 0 to L and ea, and this square would be a1 square plus 4 a1 a2 x and plus 4 a2 square x square dx. So that's the first term, minus of course second remains as it is, a1x plus a2x square q dx. So now if you look at this, I a1 a2, after now you carry out the integration, half of integration 0 to L, and then you have, yeah, no, let me carry out now the integration, so I will not write this. EA is constant, we are taking constant long length, so half will be there, EA is there, and then the first term would give you a1 square into L, and the second term will give you, I know the integration of that is going to be x square by 2, so it would be 2 a1 a2 into L square, and the last term would be 4 by 3 a2 square into L cube. So that's the integration terms there, minus you will have, here a1 L square by 2 plus a2 L cube by 3 into q. So this is what is going to be your I. Now for minimum of I, for minima of I, we have two conditions, del I by del a1 equal to 0. So that will give you, when you differentiate this with respect to a1 partial derivative. So the partial derivative is half ea will be there, and the first term would give you twice of a1 into L. This will give you twice a2 into L square. This is in terms of a2, so that will not contribute, minus no, the first term, so we will have ql square by 2 is equal to 0. So this is one equation. Of course I am not going to solve these equations, you should solve them, and del I by del a2 similarly equal to 0 will give you half ea will be there, and then the derivative with respect to a2 will give you twice of a1 L square. So derivative now with respect to a2, plus we will have 8 by 3, because no, this is a2 square, so 2 into a2 will come, so 8 by 3 a2 into L cube, and from this we will get minus q L cube by 3 equal to 0. So now you can solve these two equations for a1 and a2. Solve for a1 and a2, and then no, once you do that you get the solution. So this is how no you use the Rayleigh method, basically the integral functional and Rayleigh method, to find out the approximate analytical solution. So similarly, as a homework problem, I am giving you this. So similarly, solve beam problem. No, that is the for beam we have already derived the integral functional, and we have solved this problem using weak form also, and the weighted residual method also. So problem done earlier using weak form, weighted residual method. So please do this. Yeah, so now I think with this I come to the end of approximate analytical solutions, and now let me move on to the finite element method. So first let me discuss some basic terminology which we would be using over here, and then we will formally discuss how we develop the element level governing equation, how we assemble, how we solve problems, how we do post processing. So I will discuss all of those. So yeah, hello. Are there any questions so far? Anybody? Any question? Hello, am I audible?
Yes, sir, you are audible.
Okay. So now let me start with the finite element method. So I know we have already done this approximate analytical solution. So you have seen that we assume an approximate solution which is valid over the entire domain. So that is from x equal to whatever problems we discussed. The solution is valid over the entire domain from x equal to 0 to x is equal to l. But in case of finite element method, we do it. We still are trying to find out an approximate analytical solution, but it is piecewise. That means we divide the whole domain into smaller subdomain and assume an approximate solution within each subdomain. And so we call that as, based on that whatever solution we obtain, we call it as the finite element method. So basically, by definition, I can say this is piecewise. In finite element method, what we do, piecewise continuous approximate, piecewise continuous, that's good together. So piecewise continuous approximate solution of unknown field variables, field variables. So this is basically we are doing, this is what we are doing in finite element method. So it's an approximate, basically we are trying to find out approximate analytical solution, but rather than no single solution for the whole domain, we are assuming it to be piecewise continuous. So that is, from we are dividing into the entire domain into multiple pieces and assuming finding out the approximate analytical solution for each that piece. So now if I write the steps involved in the finite element analysis, so the step number one is the discretization, discretization of domain. So for 1D, the domain is just a line or a curve. For 2D, it would be area, and for 3D, it would be volume. So that we call as domain. So discretization of domain into smaller subdomains, and these subdomains we call finite elements. No, the subdomains are referred to as finite elements. And obviously, these, when we are dividing the whole domain into subdomains, so subdomains are going to be connected. So those connection points are known as nodes. So the elements, that is subdomains, elements are connected through nodes. Those points through which they are connected are referred to as actually nodes. So we have concept of finite element, we have concept of node. So once we do this discretization, then the second step is, we need to develop what are known as the element level governing equations. So we will have that in the form of stiffness matrix and the vector of elemental degrees of freedom and the load vector. So we call that as the element level governing equation. So the step is develop element level element level governing equations. So these we can do either, no, most of the time weak form, based on or using the weak form, or integral functional, Of course, no, you can also use the other method. So we could also use this method of least squares and collocation methods, point collocation and subdomain collocation. They can also be used, but most of the time we use either the big form or the integral functional. So that's the second step. And once we, because now we have divided the whole domain into smaller subdomains, and for each subdomain, that is each finite element, we are developing the element level governing equations. So we will have to then assemble them. So then third step is assembly. So we have to combine all these equations. So that is the summation process. So assembly of the third step is assembly of the element level governing equations of all elements. So that's the third step. The fourth step is now see what we do in case of approximate analytical solution, either based on weak form or the integral functional. We try to satisfy the essential boundary condition a priori, but we don't do that in the finite element. At the element level governing equation, we do not impose the boundary condition. We just develop the equations, then assemble, and after assembly only we impose the boundary condition. So the fourth step is imposition of boundary conditions. And the first step is, after we impose the boundary condition, we solve these equations. So these equations are now for static problems. So when we are talking about statics, so in statics, essentially the what you are going to have, the element level governing equations are going to be algebraic equations. So we solve those algebraic equations. That's the next step. So solution of simultaneous, and of course if it's a dynamics problem, then the finite element will give you ordinary differential equation in time domain, and then you will have to solve them. So solution of simultaneous algebraic equations. And then the last step is post processing. So in the post processing, what we do is the computation of strains, stresses, reactions. So these come under the post processing. So yeah, these are the six steps which are there in the finite element analysis. Any finite element analysis you carry out. Now one is that you solve by you develop your own code and implement the finite element method. So that's one way. Or there are a large number of packages. So usually in the packages, what you do, so when you are using a finite element package, so if he means finite element packages, the software, and these packages, they, for example, you have one ANSYS, you have Abacus, you have Misa, Nostron. So there are so many, COMSOL. There are so many packages. So no, everything is done. No, you have to just learn, and so there are so many packages. So if you are using a package, so then the usually step one in the package is referred to as pre-processing. So pre-processing would involve creation of the geometry, discretization, and pre-processing. No, you basically create the geometry in the form of lines, areas, volumes, and then you discretize that. So that is known as pre-processing. And these steps, basically 2 to 5 in the package, are usually referred to as solution. So right from the development of element level governing equations. So already these packages will have subroutines, so it simply calls that subroutine and gets the element level governing equation, then assembles them, imposes the boundary condition, and solves the final set of simultaneous equations. So that all is put together is known as solution. And then if you look at the step 6, is referred to as same post processing. So this is what is done in the various kinds of these packages: ANSYS, Abacus, Nisa, Nastran, COMSOL, and there are many others. So most of the time, of course, you end up using ANSYS or Abacus. That is what in the our institute we have ANSYS licenses, Abacus, and COMSOL also is there. So you can use any of these packages. And maybe I think in the Directorate of Naval Design also I know that they are using ANSYS. So I know if you learn and you happen to work in D&D, then you might actually use ANSYS for doing the structural static analysis, dynamic analysis, free vibration, force vibration, and so on, for designing these submarines and ships, various components of those and other parts, piping and the supports and isolators and things like that. So you would use these packages. Now the type of finite elements, if you look at what I mean by type, is that 1D, 2D, and 3D. So you will have no type of finite elements. So you have basically these elements are classified into 1D element, 2D elements, and 3D elements. So when you talk of 1D, so we are going to know when we are the theory part we are going to do. We will take example from all these 1D, 2D, and 3D elements, all types of elements we will be discussing. So if you look at the 1D elements, so what is the main difference? 1D means one of the dimension. If you look at the structure, now you look at the stiffener, in the submarine or a ship, and you will find that compared to length of the stiffener, the cross-sectional dimensions are much smaller. So that can be modeled as one-dimensional, finite element. So in case of 1D elements, essentially the one dimension is much larger compared to the other dimensions. So that is one thing. And the unknown field variables are like displacements, rotations. Unknown field variables are functions of one coordinate. So that coordinate is generally along length. And length means I'm calling it as a significant dimension. That means the other dimensions are going to be much smaller than this. Significant dimension, not dimensions. And now so that's the 2D. Then 2D elements, 2D elements means again the two dimensions are significant compared to the third dimension. So maybe generally the thickness is much smaller compared to the length and width, let's say. So and the main thing in this is that unknown field variables, so the unknown displacements, temperature, fluid velocities, it could be anything. No, the finite element can be used to solve any of these problems. So unknown field variables are functions of two coordinates. So those two coordinates are along the significant dimension. Two coordinates along the significant. This is no most significant dimensions. In general, of course, in specific cases, it can be the reverse. Uh, so yeah, this is, and then the 3D essentially is that your known variables are functions of all the three coordinates, so you don't know their variation along any of the coordinate directions, any of the coordinate directions. So here you say that the unknown field variables means the displacements, temperature, fluid velocity, potential, so depending on the problem. So field variables, unknown field variables are functions of three coordinate, all the three coordinates. Coordinates means I am referring to orthogonal set of coordinates basically. So now if you look at in the solid mechanics, particularly structural mechanics or solid mechanics, that is where we are most of the time going to actually deal with. So in under 1D elements you have what are known as the truss and beam elements. Truss, beam, and frame element. So truss element, in all these the one dimension, that is length, is much larger compared to cross sectional dimensions. So the unknown displacements and rotations would be function of unknown function of only length coordinates, say x along length. So truss means axial load on the rod, beam means transverse load, so bending is there, and frame means both axial as well as the transverse loads are there. So that element is known as frame element. And then in solid mechanics under 2D you have what are known as plane stress or plane strain elements. And that is one set of elements. We have plane stress, plane strain elements. Axisymmetric, of course, sometimes we do put axisymmetric under solid, but essentially we model the two coordinate, take the displacements as unknown functions of two coordinates. So that is why I'm putting this under 2D. And then plate bending, so like beam you have in 2D you have plates. For example, if you look at the panels of ship or submarine, so different panels between the rings and stiffeners, you will have panels, and those panels are subjected to transverse pressure, water, say hydrostatic pressure. So they are going to undergo bending, and if you want to model them, then you will use actually plate bending elements. Sometimes in the packages these are referred to as cell elements, but they are actually one plate bending elements. So you have plate bending elements. And then the 3D you have what are known as the solid elements, so usually referred to as solid elements. So yeah, this is what no when you're looking at a packages, so you will have different library of elements, and you will have to choose the right element or set of right elements for solving a problem. And you will develop that understanding if you know the theory behind what are the assumptions made in the formulation of these elements. And based on that you would be able to take a decision that what element I should select for solving a particular problem, or no idealizing a particular problem. So that is why we learn the theory of finite elements. So now with this brief background, let me go to the basically the first step I already said is the discretization of the domain, so that in the packages you create the lines, areas, volumes, and then it has subroutines, so it discretizes and gives you that. So I'm not going to discuss different discretization algorithms which are used for discretizing the domains. So I'm going to put more emphasis on the development of element level governing equations, because that is what finally guides you how to choose different elements for solving different types of problems. So development of element level governing equation, that is the second step of finite element method. Element label governing equations. So now again let me write the steps here, because I think most of the time I'm today ending up writing only the steps. But yeah, those are important so that you know what are the various steps involved in this. So steps are step number one in the development of element level governing equation. So we would have already discretized the domain and selected a appropriate element, either 1D, 2D, or 3D. and then we want to develop the element level governing equation depending on its physics, whether it is a solid mechanics element or it's a heat transfer element or a fluid flow element. So you will use the corresponding physics. Physics means the physical concepts, physical laws we use, so that I call as physics. So steps involved are, first step is assume an approximate solution. So it is similar to what we do in the approximate analytical solution. So the first step is assume an approximate solution. Approximate solution within an element. So now earlier we were assuming the solution which is valid over the entire domain. Now this we are only going to do for an element, within an element or subdomain. And now when you do this, so there are three requirements which have to be satisfied. So one is known as the differentiability requirement. Differentiability requirement is as per the big form or integral functional. So whatever approximate solution you assume, it has to be at least differentiable up to the highest order derivative present in the big form or the integral functional. So this will be as per big form or integral functional. So this is similar to approximate analytical solution, integral functional or total potential energy functional. And then second is because most of the time we end up assuming taking approximate solutions as polynomials. So the second requirement is that completeness. So it has to be a complete polynomial. So whatever is the highest power of no the independent coordinate x or xy for say 2D or xyz for 3D. So all the lower order terms should be present in that. So for example, if it is a 1D problem, so in 1D we should have the constant term, then we should have the linear term, we should have the quadratic term. So if we have highest power x square, then we must have the constant term and the x term in that. Or suppose if we have the highest power of x is x cube, so then x square, x and constant term should be present in the approximate solution. So it would be like this. So now if it is a 2D problem, so you will have the unknown variables, displacements, temperature, etc. are going to be function of x and y. So if we are taking the x and y, then there should be constant term and xy should be there. Or if we are taking the quadratic term x square, xy and y square, then the constant term and xy term should be present in that. So actually, no, this is known as, of course, the Pascal's triangle. Pascal's triangle. So all the terms, that means whatever is the highest power of no these independent coordinates present in the approximate solution. So all the lower power terms should also be present. That is known as the completeness requirement. And then the third requirement is that inter-element compatibility. Inter means across the elements. So inter-element. So like you have internet and intranet. So internet is outside and intranet is inside. So inter element means across the element, and intra element means within the element. So this is, you can say, is the intra element differential continuity, and this is the inter element continuity. So we often refer to this as inter element compatibility. Compatibility. So what it states is that primary variables should be continuous across the elements. So this says that primary variables, primary variable, by now because we have done the big form and then we have seen how to identify primary and secondary variables. So primary variables should be continuous across the elements. And for this what we do is know the prime, therefore primary variables has to be degrees of freedom at the end nodes of the element, and if we do that, we can, during the assembly, we can enforce this continuity. So this is what and you these elements, based on this inter element continuity, the elements are classified into different categories. So one is C1 elements, C1 continuous element are simply C1 elements. C1 continuous element are simply C naught element. C naught are no, sorry, C naught, not C1. This is C naught. C naught continuous element are simply C naught element. So in these type of elements, you will have primary variables only as the variables, not their derivatives. So we say only field variables. Field variables are continuous across the elements. So such elements are known as C naught elements, are C naught continuous elements. Then we have, most of the time we use another one, C1 continuous elements are elements. So I just say element, a single element. So these are field variables, and their first derivatives. As no, C naught means no derivatives are not continuous, only the variable is continuous. C superscript, no, this naught is superscript, one is superscript. C1 means C for continuity and one for the derivative, so first derivative. So in this case, field variables and their first derivatives are continuous across the element. And when we discuss the individual elements, I will be explaining all these concepts again to you. So this is the two you can have C2, C3. Of course, most of the time you use either C0 elements or C1 elements, but you could have elements C2, C3, and so on. So for example, if you look at the truss element, so truss element means you will have two noded truss element. It's a 1D element. You will have uh, 1 degree of freedom at each node. That is value of the displacement along the length of the beam. So we will be enforcing the continuity of this U when we have the assembly of element. This is a single element. When we have assembly of these elements, so we discretize the entire domain into many elements. So the each edge element, this element 1, 2, 3 and 4, and these are the nodes 1, 2, 3, 4 and 5. So when we look at the node 2, so whether we come from element this side or second element side, we will have same value of U, so that means U is continuous. Similarly at node 3, whether we come from element 2 or element 3, we will have the same value of U. So that is what is the meaning of continuity of U, that is C naught continuous. So this is a C naught continuous element, continuous. And similarly, if you look at the Euler-Bernoulli beam element, we are going to discuss these elements, of course, in much detail. So in case of Euler-Bernoulli beam element, what you do is a one-dimensional element. So we represent that by a line, and the degrees of freedom, if you look at, is the deflection v1 and the rotation. Now we will have the derivative. Now dv by dx is the derivative of v. So v is the field variable. So field variable v as well as its derivatives are continuous across the element. So this is a C1 continuous element. So you will have v2 and you will have dv by dx at node 2 as the degrees of freedom. So when you look at the basically the assembly of these elements, you have a beam and discretize into a number of elements. So 1, 2, 3, 4, 5, 6 and 7, these are the nodes, and the elements are 1, 2, 3, 4, 5, 6. These are the inside the circles. I'm putting the element numbers. So across node 2 you will have same value of v as well as dv by dx, so that you come from the element 1 side or you come from the element 2 side, and same thing at all other nodes. So this is basically a C1 continuous element. C1 continuous element. So that's the first thing, that we assume an approximate solution, and so we need, when we do that, we make sure that we satisfy the differentiability requirement, we assume a polynomial which is a complete polynomial, and also we make sure that it has number of terms such that we can enforce the inter-element continuity requirements, or we can satisfy the inter-element compatibility. Compatibility is actually denoting the continuity essentially. So then the second step is no, the second step we have just written only the first one. So the second step is, once we assume an approximate solution, so in case of approximate analytical solutions, next step was to eliminate some of the constants by satisfying the essential boundary condition. So here now in finite element, what we do, because the unknown constants like a naught, a1, a2, a3, they do not have physical meaning, so we express those unknown constants in terms of the unknown values, unknown values of the displacements, and if required is derivative at the node points. So rather than, of course, no, we don't satisfy any boundary condition over here, but we just express the unknown constants in terms of the what we call as the elemental degrees of freedom. So express the unknown constants in the approximate solution in terms of elemental degrees of freedom. Elemental, so there is a concept of nodal degrees of freedom, there is a concept of elemental degrees of freedom. So if I take this example here, nodal degree of freedom is only one, that is u1, and if you look at the elemental degrees of freedom, there are two, u1 and u2 for the element as a whole. Similarly, if you look at the Euler-Bernoulli beam element, there are two nodal degrees of freedom, v and dv by dx, and for the element there are four elemental degrees of freedom, that is v and dv by dx at node 1 and v and dv by dx at node 2. So for the starting node and in node. So now in the second step is express the unknown constants in the approximate solution in terms of elemental degrees of freedom. Degrees of freedom. So what are the elemental degrees of freedom? These are nothing, values of unknown variables. So displacements, rotations, temperature, depending on the problem. So the values of unknown variables at all the nodes of an element, at all the nodes of an element. So yeah, this is the second step, and the final and the last step in the development of element level governing equations is that we substitute this approximate solution in the weak form or the integral functional, and then by from there we get do the integration or the minimization of the integral functional, and then we obtain what are known as the element level governing equations, and with that we basically get the element level governing equations. So next is substitute the approximate solution from step 2 in weak form or integral functional and obtain element level governing equations. governing equations. So yeah, I think yes. So this is where I want to stop today, and next class we will start actually developing the element level governing equations. So I will take truss element, two noded truss element, and show you how to exactly develop the element level governing equations, and then how to assemble the equations, how to impose the boundary condition, and how to solve. So all that I will be discussing in the next class. So yeah, I want to stop here. If you have any questions and doubts, yeah, you can ask. Yeah. So are there any questions, doubts? Anybody? Whatever we have discussed so far? Okay, so if there are no questions, I am stopping. Thank you all for your attention. Thank you very much.